ready for the tennis match, Rain? You ready?
I've got some bad news.
Some bad news?
Yeah, really bad news, I'm afraid.
All the bees are gone? That'd be terrible news.
No,
I love bees.
It's just cold weather. It's now spring. They're coming out again.
Oh, actually, I can see one there.
Yeah, exactly.
Yeah, oh, that's good. We're out of Easter eggs.
Oh no, we've got loads of Easter eggs. Look, we've got a fort of unopened Easter eggs. That's
Oh,
the
you're
way
right.
we've
We should
got.
probably eat some of those, actually.
I do quite like a fort.
Dinosaurs are back.
That would be great. I think I'd ride a pterodactyl or a megalodon.
I think actually it'd be really bad, Wayne, because there's actually a couple of films how bad it would be if you brought dinosaurs back.
Oh, I'll watch them.
Yeah, you should.
No. It's quite bad news.
Yeah.
So you know the tennis tournament.
Oh,
later?
of course, yeah.
Well, I thought I'd get ready, so I put my white suit. It's not a suit. It's just shorts and a shirt in the wash. My banana for half time, and my tennis racket in the wash.
Alright, yeah, it's quick all read.
Banana went all mushy.
Yeah.
This shrunk. My tennis racket is tiny and green. I don't know why it's green.
I don't know why it's green, maybe the opposite of any toxic action, but
Yeah.
it's smaller than a tennis ball.
It is, so I can't really play tennis. That's my bad news. I'm going to have to cancel the tournament.
That is a disaster.
We'd have won anyway.
Oh,
so
yes, it's fine. So, what are we going to do instead then?
Well, we could. This is just up the top of my head now.
Right, gotcha.
But we could film a Carbon-13 NMR spectroscopy video.
You know, let's do that.
Let's do that.
Alright, so carbon NMR spectroscopy. It's mentioned in a previous video what NMR spectroscopy is, you might want to check that out, sort of get an outline.
Yeah.
But it needs something of an odd number of nucleons for the correct magnetic resonance thing to occur.
And there's an isotope of carbon. Carbon-13 is the one that we use.
Yep, and when you put it through a machine, you'll get a graph which will look a bit like this. On the x-axis we'll have chemical shift in parts per million. Yeah.
Chemical shift.
Yeah, in parts per million, which will correspond to things on the formula sheet we'll get in a minute.
Yep.
And the y-axis absorption in percentage.
And then you'll get these peaks. That's a peak there.
There is a peak, and there's another peak. So these peaks will correspond to the formula, but you need values, of course.
Yep. So we said right down the bottom here is 20, just under there. Just above that peak is 40, and right up here is 60. In an exam, it would be neatly spaced.
Yeah, the scale would make sense. And it does go the opposite way you think, which is a bit odd.
It goes the opposite way. So what do these mean then, is the question.
Yeah, well, they are showing certain amounts of magnetic resonance you need to know too much about, but they correspond to your formula book.
They do. So, in your formula booklet you'll have a carbon and a proton one. The proton one is the next video, and it don't know what carbon involved, but it'll be labelled Carbon-13 anyway. And
you'll look where your peaks line up, that have a value of chemical shift and that have a value of chemical shift, and you'll compare them. So for example, between our 20 to 40 it could be C to C bonds.
Yeah, it could be C to C bonds, it could possibly, this is a bit of overlap, it could possibly be a C to a halogen, I'm just going to put H.
Okay.
And it could possibly be a C to N, because they all overlap in this 20 to 30 part.
Yeah.
And in between the 40 and 60 part, there's the C to halogen, that overlaps there as well. There's a C to O, and a little bit of C to N. So you look at that and go, well, how on earth can you narrow that down? The truth is, with this little information,
you can't.
You can't.
So what they do is they might give you an MR, and they might give you what the actual thing is, and you have to show what it looks like.
So they'll, in this case, oh that's lucky, this is exactly like in the book.
Oh, that's good.
In this case, it said that it's propan-1-ol, so we can just look at how to get to that. They might just give you a chemical formula, as Triv said.
So this is when knowing your naming comes in handy, so you know what propan-1-ol could look like, because there's more than one way it could look. You could maybe go straight to drawing the two possibilities and think about what we're doing there.
Yep. But a propan-1-ol has got C to H bonds everywhere, but it's only got the one alcohol group, and that's going to be at the end.
Yes.
So the only place where I see a C to O bond is in this one,
which happens to be in our 40-60, so that's good.
So we can say, for starters, or we can say that there's no C to N in any of this. So these things, they're not there.
Yeah. And if you know it's propan-1-ol, there's no halogen group there, so you can rule that out as well.
Rule them out. So we know that these peaks are lining up with that and that.
And these things we call environments.
Carbon environments, so we can line it up with the graph, because this is the one between 40 and 60. There's only one peak, and there's only one thing it could be. So this peak must therefore be responsible for the C to O, which we know then bonds to a H in an alcohol, so it will be responsible for this last carbon at the end.
Yeah, and that means that you've got that bit now.
Yeah, and that'll be the end. Propan-1-ol. And I mean, this OH could be at the other side, but that's just the same thing flipped around.
Yeah.
So there should be another H on that as well.
I guess so.
So between the 20 and 40 though, there's only one possibility it could be, but there's 2 peaks.
And this is to do with how NMR spectroscopy works. It's all about how close things are and how they relate to each other.
Yeah. So there is actually 2 carbon-to-carbon bonds to make up propanol, propan-1-ol. So there's 2 other carbons. And so one of these would be for one carbon-to-carbon bond, and the other one would be responding to the other carbon-to-carbon bond.
So that one could be this one, and that one could be this one. And that's because this is less affected by the OH than that one is.
This has got the lone pair here, which is going to affect the spin on this one much more than this one, which is why it shows up a different chemical shift despite showing the same environment. And that can be useful in showing distances from an OH and the length of chains.
And sometimes they ask a question sort of in the opposite direction as we have here.
Yeah, so
they might either go ask how many peaks there would be.
Yeah.
So we could do that.
Yeah, have you got a nice example?
I have in my corner I've written something, so we'll do that.
Okay. So they like to go the other way around. It might just be a 1, maybe a 2 mark thing to say how many peaks there are.
Yeah, and then you can maybe say a few more things afterwards, but I'll draw it again a bit larger. That's quite a lot larger.
It is.
Okay,
Alright.
now we've got a thing. So how many carbon environments are there?
Well, let's just start at the top. There's a carbon up here, and so that will correspond to a carbon environment. So that, we'll just call that 1.
Okay.
So that's 1.
So if we go down here, then this is going to be differently affected because it's got the aromatic thing right next to it.
Yep. So it's closer to this than this is. It's also bonded to more things. So that will give another carbon environment to what this has. And if we go down this way or this way, it's going to be symmetrical.
Yeah, because they're both basically going separate pathways. As Wayne said, it is completely symmetrical. This will be 3, but so will this one be. Yeah.
If we go down again, the entire chemical is actually symmetrical. So these would both correspond to exactly the same as these. So we actually have 4 of these.
And that is true for the rest of the molecules as well.
Yep, so this would be the same as this one, so we can label it 2, and the bottom one is 1.
So that's nice and easy, but it's not always quite like that.
It's not. And it's worth mentioning as well, if you put this on a graph, we've got our shift against our absorption, what we just had. We're going to have 3 peaks.
We are.
So let's just say it's here, here and here. I'm not doing this accurately.
Yeah, that's fine. There's a problem with carbon NMR spectroscopy, and you might be able to see it quite clearly from here. You can't tell how many there actually is. Yeah,
so there's 4 of these, so you might have hoped that this one might be 4 times bigger than the others to show there's 4. This one would then be half of it to show these 2.
Yeah, no,
and that one
be
would be the same size because there's also 2 of them. So these 2 would be the same size, and that would be double to show the number.
But that doesn't happen.
It doesn't. It might be completely random, but the likelihood is they'll all be the same height exactly.
So you can't use that, and that is a limit of carbon NMR spectroscopy.
So you have to use other information, which is a future video when we combine this with other things, which is more like the questions you'll get in an exam.
Yeah.
So you mentioned a harder example.
Yeah, so if, for example, we had a functional group that was a bit more exciting on the end.
Right.
So what I'm going to do is
I'm running all of this off because I've no idea how much it's going to change.
Yeah, it might change quite a lot. What I'm going to do is I'm going to make this, instead of being bonded to a carbon, it's going to go to an O to an H bond.
Okay, but let's rub these peaks off because
Yeah.
it might not have 3, it might have more. Let's have a look at it.
Okay, so again we should start at the top.
Yeah, and that's going to be a carbon environment again, so that's a 1.
And similarly, this next one will still be 2.
And similarly again, if you go down, these are closer to this, they're both going to be 3, they're both going to be symmetrical. And so they're going to be a 3rd carbon environment.
However, if you go a bit further down, it's going to be different, it's not going to be the same as I'll have to make again.
Yeah, because before it was completely symmetrical about this point, so that's why these 2 are the same as this 2, but now these 2 are closer to this oxygen, so this central ring is what's affecting the different things, but now there's this as well.
So as I get closer to this, the shift will change, so that will become another group,
Yeah,
but again,
4th.
they'll still be the same because they're the same distance from it.
Yeah, and if we go down again, that's really close to there, so in red, that will be a 5th. So just changing a carbon for an OH just changes from 3 peaks to 5.
Yeah, and again, that still wouldn't show how many of each one there was. You wouldn't show 2 of those and 2 of those.
Yeah, so the graph itself can be useful, but it's not great on its own.
Yeah, and there's sort of questions they could ask you in carbon NMR spectroscopy. They might also ask, what are the other limits of it?
Yeah, well, if you have things that are pretty similar, like almost identical, lining up just by pure coincidence. Like I said, the C to C bond lined up with the C to halogen. Now if we had a C to C bond and a C to halogen, just because of different distances from an OH, they might actually line up perfectly on top of each other.
And that's very hard to tell them apart. Also, there's not very much of carbon-13 about. So when you want to analyse a substance, you have to have quite a lot of it. I think it's 1.1% of all carbon is carbon-13.
Not very much at all.
Yeah.
And then there's the usual stuff. If you bond to some sort of new chemical and don't have anything on your database, you've got nothing to compare it to, and it means nothing.
Yeah.
So that's another problem.
But that's out of the problems.
Yep, so next is proton spectroscopy in the next video, so check that out.
Yeah, we should sort out our tennis problem.
Oh yeah.